Section 5.3 is diagonalization. So we'll extend our use of eigenvectors and eigenvalues in order to diagonalize matrices. So we start by inspecting a diagonal matrix. Remember that a diagonal matrix is one in which all non-diagonal entries are zero. So anything off of the main diagonal of this matrix is a zero. There may be a zero in the diagonal of the matrix, but necessarily everything not on the main diagonal is a zero. So this is a diagonal matrix here, call it D. They ask us to find D cubed. And this is really the reason, this is setting us up for motivation for why we might want to have a diagonal matrix. So D cubed is just D times D times D, right? In terms of our matrix exponent notation. So here's the first copy of D, and then here are two written copies of D times each other. You remember what happened to remember maybe from exercises or previous examples that the product of two diagonal matrices is the product of the diagonal elements along the diagonal. So in other words, everything else is going to be zero in all other positions. Right? When we multiply first column times first row times first column, first row times second column, first row times third column, we'll get 3 and 3 is 9 as a product, and then everything else will be zero along this first row. So we end up with this 9, 0, 0 row. And similarly for the second row, third row, and the other columns. So you can carry out the details of this product on your own and see that D squared is actually this matrix. So it looks like we just square the elements along the diagonal. We still have the third copy of D to multiply D squared by. And we get what looks to be 3 cubed, negative 5 cubed, and 4 cubed. So just the cube of our diagonal elements. And this will generalize to any nth power of a diagonal matrix D. It's just a matter of calculating the diagonal elements nth power term by term. We've kind of re-emphasized the fact that a diagonal matrix cubed is just the elements of the diagonal cubed. Now that's a convenient calculation because it could really shorten the power of a matrix, right? So the big question is, how can we use this for matrices in general? We know that a matrix products can be really computationally intensive, but it turns out that if we have a diagonalization, so that we have a technique to turn a general n by n matrix into a diagonal matrix D, possibly. Some matrices A will not have a diagonal matrix D that they are row equivalent to. So if we do have such a matrix, so this will motivate, or at least extend to how we can use this nice power property of a diagonal matrix. If A happens to be able to be written in terms of this on the right-hand side, P inverse dP, then if we want, this is an invertible matrix P with its inverse P inverse on either side of a diagonal matrix D. And if we take A to the mth power, so any positive integer power, and we do this on both sides of that equation, we're going to build on the right-hand side a nice technique for calculating such a power of A. And we have copies of P inverse dP. We have m copies, or m factors of these terms. Well, if we look at the inner sides of these, P times P inverse, P times P inverse, this is sort of a common pattern within the middle of it all. P times P inverse is the identity matrix. So that'll leave m identity matrices, or maybe m minus 1 identity matrices in between all of these copies of the diagonal matrix D, or factors of the diagonal matrix D, which the identity matrix doesn't change the diagonal matrix D. So it's just m multiples of D here in the middle. So that's the matrix D to the m power. And then the only two P inverse and P matrices that don't cancel are on the outside. Remember, matrix multiplication is not commutative, so we can't just multiply P inverse and P, commuting it through D to the nth power. So this does have to remain here, and that's really the only work that there is after we found the diagonal matrix D in the matrix P, is finding the inverse, P inverse. But it's nice to see that we could find an imp power of A, a matrix A, in a simple calculation like this. We can convert it to a diagonal matrix and then use what we just saw above, that cascading cancellation in the middle. Now, how do we find such a diagonal matrix? That's the real question. Maybe one hint as to why we would want to be able to take a matrix to a power. One reason we might want to do that is in differential equations, and perhaps this is talked about, and of course you'll take soon, or maybe not, but there's a reason to, or there's a notation for writing the exponential function e to the matrix A x, right? So this is, or a x with x as a variable, I believe. I shouldn't write the vector x there. And this is called a matrix exponentiation. And it turns out, if we remember from the theory of Taylor series, we can write down e to the x as a polynomial, right? Remember that was our, if I can remember correctly what it is, it's we have the sum from n equals 0 to infinity, and it's over n factorial. And we have this argument up here, ax to the n for each of these. So remember, if that was just e to the x, there would just be an x to the n over n factorial, and we'd sum that up. Well, this is a thing we can feasibly write down right here. Right? We can write down this matrix A to the power of n. It didn't make sense to write it as this previously, or here, until we defined it via this Taylor series. So when we look inside the Taylor series, or it's actually a Maclaurin series, it's centered at 0, we realize that, well, A is going to be taken to positive integer powers n. We need some way to be able to do that. And if A is diagonalizable, then this is exactly the way to do that. Now, why would we want to exponentiate a matrix? Well, it could be the solution to a system of linear differential equations, and that would be the answer to that. So that's, again, we won't do any of this work down here, but it's just a hint as to why this might be useful, why we're curious about taking powers of a matrix A. So anyway, let's find this diagonal matrix. Let's see when one will exist, and then perhaps how to go about finding it. So we have this diagonalization theorem for an n by n matrix A. So an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. Okay, and then sort of a follow-up remark here is A equals P times D times P inverse with diagonal matrix D if and only if the columns of P are n linearly independent eigenvectors of A. So this is more, this second comment is kind of expanding on this first if and only if statement here. It's kind of just giving a further detail about what that's telling us. In this case, the diagonal entries of D are eigenvalues of A that correspond respectively to the eigenvectors of P. So the diagonal matrix D we have to know what to put in the main diagonal. We put the eigenvalues of A in the main diagonal. We'll see why in just a moment. So if we we'll give the intuition for why this result is what it is, and it's a bit of the elements to the proof of this theorem as well. So we let A be diagonalizable. So A is equal to P times D times P inverse, where D is a diagonal matrix, and D1 through Dn are the diagonal elements of D. And we let P have the column representation P1 through Pn, standard notation for a matrix, writing it by columns. And the equation A equals P times D times P inverse, if we multiply both sides by P inverse, then we've got A times P equals P times D. Right? So it's probably better we could even have started, instead of this expression, we could have started with this expression right here. And then we could derive it from, because what we don't know is whether or not P actually has an inverse unless we assume that A is diagonalizable. So what I'm writing down is just, this would be the general statement here. A times a matrix P is equal to P times a matrix D, which where D is a diagonal matrix. And if we look at that situation without assuming anything about invertibility or not, just starting here, we see that, remember, matrix times matrix multiplication is the matrix times each column vector. And that'll be apparent down here when we do A times P1 all the way up through A times Pn for each of these P column vectors. On the right-hand side, you might want to check that this is the case, but for this matrix P of column vectors P1 through Pn times the diagonal matrix D with diagonal elements D1 through Dn, we get exactly this. It's the first diagonal element times the first column vector of P, all the way through the nth diagonal element times the nth column vector of P. We could check that in a 2x2 or 3x3 case just to make sure you believe it. And if we look closely, we realize that each of these pairs, A times P1, is going to be equal to this column. So the first column of each matrix on left-hand side and right-hand side are equal, and all the way through to the nth column on each side. Well, the statement of A times P1 equals D1 P1, or for any I or any I in here, A times any of the ith column will have DI PI. This is a matrix A times a vector PI is equal to a scalar DI times the vector PI. Well, that's exactly our eigenvalue statement. So in this case, we have that DI is an eigenvalue of A with eigenvector PI. Right? And that's true for all of our 1 through n columns of P here in diagonal elements. So when we make that connection, well, the only way then that P will be invertible is if P is a matrix of full rank, right? In other words, all of its columns are linearly independent. Well, if P has all linearly independent columns and P is an n by n matrix, well, then P will span all of Rn. And, well, it'll have an inverse as well, right? I guess I'm saying a few equivalences, not all of which are necessary, but just to kind of remember whether or not P is invertible. One of the ways P could be invertible is that it has all of its columns are linearly independent, or in other words, all of its columns span Rn. And if, remember that if we look at what we're looking at, if so A being diagonalizable is equivalent to A having n linearly independent eigenvectors. Okay, so in other words, A being diagonalizable depends on whether or not P is invertible. And P is invertible if all of its columns are linearly independent. They're in linearly independent columns. In other words, and then we saw that these column vectors are eigenvectors of A. So then A has n linearly independent eigenvectors, and then we have our equivalence between the two. So this tells us, and then we can write, finally, a statement that looks like this. We could talk about P inverse, and we know that we can express A in this form, A equals P times D times P inverse. So the algorithm for doing this should be pretty clear. The diagonal entries of D will be the eigenvalues of A, and we'll write that down in order to correspond with the eigenvectors for each eigenvalue in the matrix P. So we'll see this decomposition right here suggests that, right? If we're talking about the eigenvalue D1 for A, then it's going to have eigenvector P1, and we should form the matrix P by putting that eigenvector in the first column so that it corresponds with the first diagonal entry, all the way through to next to the second eigenvalue that we write down. We should put its eigenvector in the second column. And when we get all the way down to the nth eigenvector, we should put that eigenvalue in the nth diagonal element. And that way all the diagonal elements or eigenvalues pair up with their respective eigenvectors, and we'll have that this statement is true. We have that this statement is true, then we've got this scenario. The last thing we would have to do is invert P to get P inverse, and then we could write this down in full as it is. So let's have a look at an example then. So we're asked to diagonalize the given matrix if possible. So we have a 3 by 3. We need to find first its eigenvalues. We're going all the way from the start with this, and we know nothing about it, but we want to see if we can diagonalize the matrix. So the best way to find out if we can is essentially just to move in the direction of doing so. So the first thing we need to do is to find the eigenvalues. So here is our initial matrix. We set this equal to 0. We have A minus lambda I. We're taking the determinant of that. And we set that determinant equal to 0 to form the characteristic equation. And this is a bit of a big mess, right? Of course, we've got the main diagonal here, and then this diagonal here, and then this diagonal here. And these are all of our plus diagonals. In other words, we don't change the signs of any of these. And then when we slice the other way, top right to bottom left, or 3 by 3 determinant, we have a minus sign in front of all of these. So they're grouped in brackets or braces behind that minus sign. Here's our first multiple here. Then our second multiple are these 3 products. Again, we could write this extra 2 columns if we want, or we can wrap around. That's this. And then our last multiple is this. And remember that all of those, their parity is taken care of with that minus sign in front of the brackets. And then once we group like terms, we arrive at negative lambda cubed minus 3 lambda squared plus 4. It's not a bad time to remind students about what kind of algebra tools we still have. Don't forget that we have a rational roots test or rational roots list that we can write down. And that list is always given by all the factors of this number, of this coefficient, the constant coefficient, divided by all the factors of this leading coefficient. So that's all the factors of 4 divided by all the factors of -1 with plus or minuses, right? So the possible rational roots for this polynomial are plus or minus 1 and plus or minus 2, because those are the factors of 4 over 1. If we trial and error check, we realize that lambda equals -2 is a root of this polynomial. When we plug in -2, we get 0. So we use synthetic division by -2 using the coefficients of this polynomial over here. And remember that synthetic division works as follows. -1 comes down here. We multiplied -2 times -1 to get 2. Then we add this column. We get -1. Then -2 times -1 gives us a 2. Then we add that column. We have 2. 0 times, or -2 times 2 gives us a -4. 4 and -4 gives us a 0. So this synthetic division confirms, by the fact that the remainder term is a 0, confirms that -2 is in fact a root of the polynomial with the coefficients being these values. Remember, we put a 0 in place for as a placeholder because we don't have a lambda term in here. It's plus 0 lambda. And it also tells us what the remaining values are. If this was a lambda cubed polynomial, cubic, then this is a quadratic down here, and this will be negative lambda squared minus lambda plus 2. And that's what we write down in the next line's factorization. So, and it's all times lambda plus 2 because we factored this linear factor out via synthetic division, using the root to factor the polynomial by synthetic division. Or you can use long division if you prefer, or you can use a formula to factor a cubic polynomial, but nonetheless, there are lots of algebraic tools around. It doesn't hurt to see a reminder of what's available. This last step factors this polynomial into 1 minus lambda times lambda plus 2, which leaves us with 2 factors of lambda plus 2. So we have a repeated eigenvalue, a repeated root, and we have 1 minus lambda as our other root here. So we have a root of -2 from this root, and from this linear factor, and then a root of 1 from this one. So there's our eigenvalues on this list. Now we need to find the eigenvectors corresponding to each. So in that case, what we'll do is we'll take the matrix A minus -2i. So A minus lambda I here is going to be A plus 2i. The double negatives cancel. So we just add 2 along the diagonal for the matrix A, and we'll put it into reduced echelon form, which we arrive at here. And from the top row, we see that, well, we only have one basic variable, and that's x1. x1 is equal to x2, negative x2 minus x3. Remember, we're solving for the homogeneous equation there. There's an augmented column of zeros that is understood. And what we arrive at as a solution here is the following. x2 and x3 are free, that we don't have basic variables, we don't have leading entries anywhere else but this first column. So these columns have no leading entries, so they're free variables. Now, decomposing this as an x2 multiple and an x3 multiple, we have the following two vectors to represent our eigenvectors or solutions to the homogeneous equation. Note that these two vectors are linearly independent, and they're going to suffice to be two different eigenvectors. In fact, the span of these two vectors is exactly what we have written here. This is a linear combination of free parameters x with free parameters x2 and x3 of these two vectors. So that's literally just the span of these two vectors. But we'll use each of these two vectors to construct our matrix P by the time we're done with this problem. So we still need to find the eigenvector for lambda equals 1. We have A minus 1 times the identity matrix. Well, that's just A minus I. So we have down the diagonal, we've already done the subtraction of 1 for each element. This is what we get right out of the gate. By the time we get to reduced echelon form, we see that we have 2 basic variables. X3 is a free variable because it does not have a pivot position in its column. So we do have 1 free parameter. X1 is equal to X3, right? Remember again, because there's a column of zeros on the right in the augmented matrix that we could write down, and then we could solve for X1 and X2 in terms of X3 and get these equations. And then writing this, so X1 is X3, and then X2 is negative X3, and then X3 is just itself. We get this vector as well. So now we've got 1, 2, 3 eigenvectors corresponding to our 2 eigenvalues. One of the eigenvalues had 2 eigenvectors. And when I write down my matrix P, I'll use the 2 eigenvalues for the eigenvectors for the eigenvalue -2 in order. First 2 columns are the eigenvectors for the eigenvalue -2. I put -2 twice, right? Once for each eigenvector that it has. And then my last column is the eigenvector associated with the eigenvalue 1. And that's how we match up all of these elements. Now, it doesn't really matter which order we do it in. If we move column 3 and P to be here in column 2, then we should move column 3 in the diagonal matrix to be in column 2 as well. No reason to do that, but it's just good to note that the order doesn't matter as long as each of the columns in P correspond to their eigenvalues in D in the diagonal. So what we can check is that with this matrix P and this matrix D, that A is equal to P times D times P inverse. And if you don't want to invert the matrix P and you're not asked to do so, and you don't have to find it, so you don't need to find P inverse, one way to check that this is true is maybe just to say A times P equals P times D. So maybe just do that product, and you can use only the matrix P that we already have, and you'll see that this should hold just as well. And then you don't have to find the matrix P inverse. How did we get from here to here? Well, we multiplied both sides by P on the right. So we have A times P on the right, PD P inverse times P on the right left us with PD on the right-hand side. So that's maybe a nicer way to check this without having to invert a matrix, even though that check will still be somewhat complicated. So it turns out we found a diagonal matrix such that this is true, right? And generally what we'll find is as long as we have as many eigenvectors as we do columns in our matrices, well, then we'll be just fine. So for n by n matrices, as long as we have n eigenvectors, in linearly independent eigenvectors, remember that for each of these free parameters, we will get an independent eigenvector. So as long as we have that, then we know that we can diagonalize the matrix. There's a chance, and we'll see in another example, that when we arrive at this position, we'll have maybe just one free parameter, and we'll just have one linearly independent eigenvector, and we'll just get one here. And if that's the case, we don't have enough eigenvectors to make up a matrix P. So then we see that A is not diagonalizable. And the categorization for non-diagonalizable matrices is a little bit more complicated than it being diagonalizable or not, because some matrices may not be diagonalizable, but there are ways to come up with other semi-diagonalized forms of them. And I'm making that term up, but it's reasonably that's a reasonable description of the situation. I don't believe we'll get into any of those cases in this course, but know that it is out there. So we'll diagonalize the given matrix if possible once again. So same thing, A minus lambda I, take the determinant, set it equal to 0 to get the characteristic equation. And when we put all of this together once again, we arrive at the same exact polynomial, oddly enough. And we have as factorization the same thing that we had on the previous page. And then we see that our eigenvalues are -2, -2, 1. It's not uncommon if if an eigenvalue has multiplicity more than 1, then you list it as many times as its multiplicity. Right? So -2 has multiplicity 2, so I listed it twice. And that's just maybe just small convention and notation, just so we see, okay, we have -2. It's got multiplicity 2 because it's written there twice. It's a little bit quicker and easier than writing -2 has multiplicity 2 on the page. So you just list it twice and realize that it has algebraic multiplicity 2. So same thing, we need to do A minus -2I. This is actually lambda, it should say I. It's all right. So what we're doing is just adding 2 along the diagonal. And we get a matrix that looks like this, and then we put it into reduced echelon form, and that puts us here. So our reduced echelon form of this matrix, we have 2 pivot positions in this matrix, one in first column, one in the third column. And that means x2 is free. And then solve for x1 in terms of x2. And we see that x1 is equal to -x2. And x3 is equal to 0. Remember, again, there's a right-hand side or an augmented column of zeros there. So x3 is 0, x1 has to be -x2, and x2 is free. Right? So that would be -x2, x2, 0 for matrix, and then we factor the x2 out, and we'll just use this column. Remember, so that might raise the question at this point, we can just pick any old eigenvector from this set. Remember, this is a span. If x2 is free, there are infinitely many eigenvectors in this space, or infinitely many solutions to this homogeneous problem, or again, infinitely many eigenvectors. It doesn't matter which version we pick, right? We saw before that for any multiple of an eigenvector, A times this vector x is still going to be equal to 2 times this vector x, no matter what x is, as long as it's a multiple of -1, 1, 0. I think we saw that when we first introduced eigenvalues, eigenvectors. So towards the bottom here, we need to keep going. We've only got one vector. This is going to be possibly bad news for us, right? We're going to have a question at the end of this. And we need to find the eigenvectors for lambda equals 1. Well, A minus 1 times I is A minus I. And there's the changes down the diagonal that are made here. We put this into reduced echelon form. And again, we find x1 and x2 are basic variables. x3 is free. And when we solve for x1, in this equation up top, remember again, zeros on the right-hand side, we have x1 is equal to x3. We have x2 is equal to -x3. And we have that x3 is free. So when we write this vector down, we'll have 1, -1, 1 times x3 is a free parameter. And again, as I justified before, all we need is this basic version of the vector 1, -1, 1. keep it as simple as possible. It's just nice and clean. We don't no reason to multiply this vector by 1000 with x3 here and use that as our column in P, even though that would be perfectly suitable. Well, then we go to diagonalize this, and we realize that we only have 2 columns for P. P is supposed to be a 3 by 3 matrix, and we've only got 2 columns for it. That's somewhat problematic, right? So what we've realized is that A is actually not diagonalizable. So that's our conclusion in this case. We only have 2 matrices here. So A is not, in fact, diagonalizable. Remember over here we had 3 vectors total for our 3 by 3 to build P. And so it worked out. And even though we still have our 3 eigenvalues that we could put into a diagonal matrix, we don't have a second eigenvector to go with our repeated -2 here. We only have 1. So we're sort of at an impasse there. We just have to conclude that A is not diagonalizable. And this is exactly true. There are other forms, like I said, that are near diagonalizable. And there are ways to come up with -2 might actually have, we might be able to generate yet another linearly independent eigenvector for -2, but that's called a generalized eigenvector. And it's a quick and not so hard technique to do so, but it will not make I diagonalizable. It will make it, it'll put it into one of the canonical forms that we might discuss in a deeper linear algebra course or in another course in algebra. So for us, if we don't have eigenvalues immediately or eigenvectors, a sufficient number of eigenvectors for all of our eigenvalues and their multiplicities, then we just conclude A is not diagonalizable. And that's true. We just don't pursue any of the more complicated forms. So an n by n matrix with n distinct eigenvalues is diagonalizable. So this follows more or less from one of the previous results. An n by n matrix with n distinct eigenvalues. Well, remember that distinct eigenvalues yield linearly independent eigenvectors. That's back in section 5.1, maybe 5.2. One of our previous sections in chapter 5 lets us have that fact. And if we have n linearly independent eigenvectors, well, then we know that we're going to have a diagonalizable matrix A. So that's one way to know. It's a quick and obvious. If all the eigenvalues are different from each other, then each one is going to contribute a linearly independent eigenvector to the set of columns for the matrix P, and we can diagonalize A. So determine if this matrix is diagonalizable. Well, we don't always have to pursue that through the method of diagonalization. In this case, we have an upper triangular matrix. All the values below the main diagonal are 0. So this is an upper triangular matrix, and then we just recall that the eigenvalues of any triangular matrix, upper or lower, are just the diagonal elements. So along the main diagonal, we have the elements 7, -6, 1. So those are our eigenvalues since this is a triangular matrix. Again, this won't work with a non-triangular matrix, so be careful. Notice on the previous problem, we had 2, -6, and 1. And when we wrote this down initially, we had some factors that were 2 minus lambda, -6 minus lambda, 1 minus lambda. And in the end, we didn't get, well, some of these maybe, -2, well, that actually doesn't. It's not a root to this. So that doesn't really correspond to that. The only one that does, and that's just out of some luck with this matrix, is the 1. So maybe there's no reliable way to use these expressions along the main diagonal in this to really know what the eigenvalues are going to be. And we see that, yeah, in this case, 2, -6, and 1, the main diagonal elements were not the eigenvalues, except for one sort of lucky coincidence of the value 1. And that generally won't happen in any reliable or predictable way unless we have a triangular matrix. So again, if you're not sure of that, then go ahead and carry out the process of finding the eigenvalues of this matrix. Do A minus lambda I, set it equal to 0, take the determinant, or set the determinant equal to 0, and solve for lambda, and you'll find that you still get this. So they're distinct eigenvalues. In other words, 7, -6, and 1 are different from each other. This is an n by n matrix or a 3 by 3 matrix with 3 different eigenvalues. So we know that it is diagonalizable because it's going to have 3 linearly independent eigenvectors, one each from these eigenvalues, and we can form the columns of P for the diagonalization of A, and we conclude that A is diagonalizable. And if you wanted to, you can carry out the details of actually diagonalizing it. But, it's not any different than the process we did on the previous page. So our last result in this section is it's a nice set of facts to have around when we're working on these problems. I'll describe some of the intuition behind it, but the proofs can be a little bit challenging, and I think they might lean on some later results in the textbook or in the course. So if we have an n by n matrix whose distinct eigenvalues are lambda 1 through lambda p, so notice I'm not saying lambda n, so maybe some of the eigenvalues have algebraic multiplicity greater than 1, so some might be repeated. For any one of our lambda k's, so any lambda on this list is what that's telling us, the dimension of the eigenspace of any given eigenvalue is less than or equal to the multiplicity of the eigenvalue. So in other words, if we have, say lambda 1 has multiplicity 3, so it's lambda minus 1 cubed as part of our linear factorization. So the value 1 has multiplicity 3. It's an eigenvalue. It's an eigenvalue of 1, and it has multiplicity 3. So the most number of eigenvectors it can have, the most number of linearly independent eigenvectors it can have is 3, right? It can't exceed its multiplicity as an eigenvalue. And if we thought about it, then yeah, if we'd have to be careful. If perhaps all of these eigenvalues, we had n minus 1 total distinct eigenvalues, and then lambda 1 was repeated twice, right? We had lambda 1 was equal to perhaps 1, like I said before, and it had a multiplicity 2. But say it had 3 eigenvectors going along with it. If it had 3 eigenvectors going along with it, and then every other one of these eigenvalues had 1 eigenvector going along with it, we'd exceed the number of columns we could fit into P. We'd also exceed the number of linearly independent vectors that could be in a set. There'd be n plus 1 linearly independent vectors in a set of n vectors that are from Rn, and that we know is not possible. If we have n plus 1 vectors that have n entries each, then we know that we have a linearly dependent vector in there somewhere. So arguing something somewhere along these lines could be part of the proof of this. Now this is just giving a sketch for the intuition of it. So we just had we can rely on this fact that each eigenvalue is going to have no more eigenvector, a dimension, an eigenspace dimension that's no greater than its multiplicity. So in other words, if we go back to previous examples, we saw that in this case, remember we had the eigenvalue 2, or -2 rather, and it has, well, the dimension of its eigenspace is 1. It has 1 linearly independent eigenvector. It didn't have a second one. This one, on the other hand, this version, lambda equals -2, had 2 linearly independent eigenvectors. It has an eigenspace with dimension 2. So in either case, we've satisfied what the theorem tells us. -2 has multiplicity 2. It can have up to a dimension of 2 for its eigenspace, but no more. And we've seen 1 and 2 cases, or the case where it's dimension 1 or dimension 2 by those past 2 examples. Can it have dimension 0? Can an eigenvalue have dimension 0? Well, no, that wouldn't be the case, right? Because that would mean that only the 0 vector satisfies that solution, which means that A minus that lambda times I would not have a non-trivial solution. Remember that that's part of the requirement for lambda to be an eigenvalue, is that it actually, in fact, has a non-zero eigenvector. So all of these eigenvectors will have eigenspace from 1 up to its multiplicity, or somewhere in between. Okay, the second statement, the matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspaces equals n. So in other words, for each of our eigenvalues that we have, if we sum up the dimensions of their eigenspaces, we need to amount to n, right? Well, that makes sense. We need n linearly independent vectors to constitute our matrix P. So that needs to come from eigenspaces whose dimensions sum to n, and that sort of relates this this equivalence to what we already know. So this happens if and only if the characteristic polynomial factors completely into linear factors. In other words, we don't have an irreducible quadratic in there when we're dealing with the characteristic equation or polynomial. And then secondly, once it does factor completely into linear factors, the dimension of the eigenspace for each of our eigenvalues in this list is equal to the multiplicity. So remember what happened before. The multiplicity of -2 was 2, right? It occurs twice in here as a root. And it actually had 2 eigenvectors. It had, in some sense, it had a full eigenspace matching its multiplicity of 2. So dimension 2 of the eigenspace matched the multiplicity of the root. In this case, -2 was an eigenvalue with multiplicity 2, but its eigenspace was only 1. Its eigenspace did not match its multiplicity, and this is where we have a breakdown that's being sort of pinpointed by this result in B right here. So this is that's B as a summary of diagonalizability of A. Now, the last statement C is if A is diagonalizable and BK is a basis for each of our lambda k. So if we write down all of our bases for all of our eigenvalues, then all these bases together should form an eigenvector basis for Rn. Well, that's hardly different than what we've been saying. If we have n linearly independent vectors that all come from our collection of eigenvalues, maybe multiple from some of our eigenvalues, but matching their multiplicities, as part B suggests, then we know with n linearly independent vectors, we have a basis for Rn. If these are all eigenvectors, then yes, it's an eigenvector basis for Rn. So nonetheless, this is a nice theorem to come back to and just sort of check to make sure that, if you're trying to diagonalize a matrix, that if you're able to do so, then yes, it's usually if you're able to do so, it's easy. You can just check to make sure that the diagonalization you've suggested actually holds, and then you don't really worry about it. But if you come to a point like this and you're not sure, well, should I be able to diagonalize it, or what's really the problem here? This theorem is a nice way of telling us whether or not we can walk away from it and claim it's not diagonalizable. Or as a shortcut, we might not have to diagonalize something if we just come up with, if we know facts about the eigenspace of each eigenvalue. So that's it for section 5.3. Primarily, you'll be diagonalizing matrices. Probably a lot of the theoretical or conceptual questions could be answered from this theorem here. In section 5.5, which is the next one we'll cover, we will talk about complex eigenvalues, which is something we haven't seen yet, and that'll sort of complete our consideration of eigenvalues and eigenvectors.